Uh, so let us continue our lectures devoted to stochastic calculus for Gaussian functionals. Let me share my screen. Here is my screen, and okay. So today we continue discussing the expansion with respect to Hermite polynomials for functionals from Gaussian random variables. This expansion has a special name, and we begin with this name, Ito-Wiener expansion. We will see why these two names are related to the expansion via orthogonal polynomials later. Let me recall you what we did last time. We considered a random variable which has standard normal distribution. We introduced the sequence of Hermite polynomials via such definition. Hk of x is equal -1 in k power e minus x squared over 2. Here is d over dx k, excuse me, d over dx e minus x squared over 2. And we have seen that arbitrary random variable eta, which is square integrable, and measurable. With respect to psi, has a unique representation of the following kind. Eta is equal to sum from k equal 0 to infinity ak hk of psi. This representation contains orthogonal summands, namely expectation of eta is equal to a0 and expectation of eta square is equal to the sum from k equals 0 to infinity k factorial ak square. Based on this summand, on this representation, we considered a special function like stochastic exponent. So we defined e of x is equal to exponent of x, exponent of x psi minus x squared over 2. And we have seen that this random variable has a very nice expansion via Hermite polynomials, like the series x factorial, xk k factorial hk of psi. Due to this, one can define the special transformation of variable eta from x. It is expectation of eta multiply on ex, and it was equal to the sum from k equals 0 to infinity ak xk. From here, one can see that this transformation is analytic function on the all real line, and using its derivatives at 0, one can get the expansion of eta with respect to Hermite polynomials. And finally, we defined a weak product of two random variables, alpha, beta, in such a way that tau alpha beta of x is equal tau alpha x multiply on tau beta x. But from the first point of view, this material looks like interesting and beautiful algebra, and has a very weak relationship with the usual stochastic calculus and analysis of random processes like even Wiener process or some Gaussian processes. And our aim is to make the bridge, is to understand that these tools which we discovered last time can be expanded on the case which is more applicable, like a case when we will have functionals from infinite family of Gaussian random variables. So this is the first step which we will do today. Instead of xi, instead of one Gaussian variable, xi, consider a sequence of IID and 0, 1 random variables, xi n is greater or equal than 1. Then suppose that our sigma field, you remember we have omega fp probability space, and f is a sigma field of random events. So I will suppose that it is generated by the sequence xi n. And now I am considering a random variable eta, which still is square integrable, and our first aim is to say what is the orthogonal expansion. Eta equal to sum of what? From k equal 0 to infinity, and here what we have to place there. Of course, it looks like that here we have two problems, not one, but two. The first problem is the following, that even if we increase the dimension from one random variable xi to several random variables, finite number, but several random variables, xi1, xi d, for example, then still we have a new problem. we have to understand what will be a multidimensional Hermite polynomials. And we have another problem which is related to the fact that we consider now an infinite number of Gaussian random variables psi n is greater or equal than 1. It occurs that the last problem can be solved relatively easy, so we will start from the first one. Instead of have the sequence, we consider firstly case of finite number psi1, psi d. So suppose that this is a standard Gaussian vector in Rd. Namely, it means that psi1, psi-d are independent standard normal variables with zero mean and variance equal to 1. Then one can look for orthogonal expansion of square integrable random variable eta with respect to Hermite polynomials, so from psi1, psi-d. Now it is more or less clear how to organize it. Namely, suppose that I have k1, kd, which are greater or equal than 0 and integer numbers. Then I can define multidimensional Hermite polynomials like following. H, let me, for a moment, k1, kd from the vector x simply as h k1 from x1, h k2 from x2, and so on. H k d from xd. Since the suitably normalized Hermite polynomials are the orthogonal basis in L2 with respect to standard Gaussian norm, then it is clear that the family of such random such functions like k1 factorial squared and kd factorial h k1 kd k1 kd greater or equal than 0 is an orthogonal basis in L2 Rd, and here we put standard Gaussian density 1 over 2 pi in d power multiply on e minus norm of x square over 2 dx. Okay. This is just a consequence of the fact that one-dimensional Hermite polynomials suitably normalized organize the orthonormal basis in L2R with the standard Gaussian measure. Due to this, we are ready to get the orthogonal expansion for square integrable functionals from our random vector xi. Namely, if we have some agreement that our sigma field is generated by xi1, xid. Let me recall you that we consider finite case of the case when we have just finite number of initial Gaussian random variables. Then for any eta which belong to L2 omega fp, we have the following unique expansion. Eta is equal to sum from k1, kd equal 0 to infinity, a k1, kd, and here h k1, xi1, and so on, h, kd, xid. From the first look, it seems that we totally solve the problem of expansion of square integrable random functionals from our standard Gaussian vector and can go further. But to go further, it is convenient to invent good notations for further considerations. Namely, in view to future application, it occurs that we have a very bad form of our orthogonal expansion. It is true, it is good from the point of view just theory. We have a constructed orthonormal basis, but it is not satisfactory from the future applications. For example, we will see that we will need the infinite number of Gaussian random variables related to, for example, Wiener process. And in this case, it will be very hard to understand the infinite sum with respect to all xi of these products of Hermite polynomials. So it is natural to ask for more beautiful form of this expansion. To do that, it is convenient to start from the function which we already introduced in the previous lecture and call it by stochastic exponent. So let us try to understand which kind of expression we have for stochastic exponent. So let us consider E of now of x, where this is a vector, and I will write the form of this stochastic exponent. Just keeping in mind the one-dimensional case. You remember, in one-dimensional case we have Ex is equal to exponent x xi minus x squared over 2. This was a one-dimensional case when d equal to 1. Yeah. So I will try to do the following. Since in the orthogonal expansion we have a products of Hermite polynomials from every coordinate psi1 so on to psi d, then I will try to organize the stochastic exponent in multi-dimensional case also as a product of corresponding stochastic exponents. Yeah. So let me try to do this. So Ex will be a product, and I will take this product under one exponent, like the following. Here is the sum from k equal 1 to d x k xi k minus, again the sum, k1 to d, here is xk square O2. And this sum in the brackets can be, of course, rewritten using the notations from the geometry in RD. So it is equal to exponent. Here is a scalar product, x, xi, and a minus norm of x square over 2. Here I use Euclidean scalar product and Euclidean norm in RD. Okay, this is the expression for stochastic exponent, and of course it is very easy to get the orthogonal expansion now, because here we have a product, as we said, of one-dimensional stochastic exponents. So I can continue writing and just have the following expression, like the sum from k equal 0 to infinity. Here is x 1 in k1 divided over k1 factorial, multiply x 2 k2 divided over k2 factorial, and so on. Here is x d in kd power divided over kd factorial, and multiply on h k1 from xi1 and so on, h kd from xid. This is the expression for stochastic exponent, and now we are even able to define our transform tau eta of x, which is equal to expectation of eta with e of x, as follows. It is equal to the sum from k1 kd equal 0 to infinity. Here we have h k1 kd. Here is x1 in k1 power, xd in kd power. Okay, and when we write this in such a way, one can understand that maybe this is a source for us how to rewrite this sum, because here we have analytic function of from d variables, and as usual, analytic function is expanded in the in power series. But usually in power series, we have the sum related to fixed powers. Yeah, so we must to rewrite it as follows. It is equal to sum from n equals 0 to infinity. It will be power. Now, I am collecting the members of the previous sum related to the power n. Here I will have the following: k1 plus kd equal to n, and here is AK1, KD, X1 in K1 power, XD in KD power, yeah? And we put here brackets in order to emphasize that now we have the order summation with respect to powers of our polynomials, yeah? So inside of brackets, we have a homogeneous polynomial of the degree n, yeah, of the degree n. So one can even rewrite this polynomial. One can even rewrite this polynomial with the following help. So let us consider this summand separately. This sum from K1 plus KD equal to n, A, K1, KD, X1, K1, XD, KD power can be written as follows. Can be written as follows. It's equal to. Let me put here firstly notation. Then we will see what does it mean. I will put here. I will put here the following notation. C n from x1 x. Here is n I, where Cn will be the following mapping from Rd multiply on Rd to Rd is n linear form. Oh, excuse me. To R. Is in linear form. And since we put here x at every place, then we say that it is symmetric. How I can relate this expression to the previous one? I will suppose that Cn is expressed in the natural basis E1 ED as follows. Cn is equal to sum from J1 and Jn equal 1 to D. Here is C J1, Jn E1, EJ1, EJ2, and so on, EJD, JN. Okay. And now Cn from X is equal to sum from J1, Jn equal 1 to D, C, Jn, J1, Jn, X, J1, X, J2, and so on, X, Jn. Now, how to jump from this sum to the previous one? We just have to collect. The variables which are the same. So we have to rewrite this part like x1 in k1 power multiply x d in kd power. So you see that we can have the representation of the previous sum in a very nice form, which is more suitable and more convenient because it is natural generalization of just power in one-dimensional case. Since then, I will try to go back to this expansion for eta, and also use the same approach. In order to do this, let me expand our definition of weak product. I will say that for psi I and psi j, when I is not equal to j, the weak product of phi from psi I, psi of psi j is equal just to usual product. Phi of psi I, psi of psi j. Let us use this property for a moment. It occurs that when we define this in such a way for independent or different psi I and psi j, it will lead us to very good definition of weak product in the future. So I will suppose that it is true. Then I will introduce the notation Cn psi1 from psi. Here is n time. This is by definition is the sum Jn equal 1 to D, C Jn G1 Gn multiply on the psi Jn psi J2 and so on psi Gn. This is our definition of the action of polynomial form on our standard Gaussian random vector. You see, instead of multiplication in there, we use here weak product. And maybe you understand that due to this weak product, we have Hermite polynomials. So one can see that if we consider some examples, for example, that psi1, psi2, psi1, and psi3 is equal. I just have to unite this one. And I know that weak product of psi1 and psi2 and psi1 is equal to h2 of psi1. Now multiply psi2 and psi3. Psi2 and psi3. So what we are doing, actually calculating this weak product, we collect the same random variable, organize the power, and change this power onto corresponding Hermite polynomial. Exactly here we collect psi1 and psi1 two times, and instead to write psi1 square, we just write Hermite polynomials of the same degree. This is the idea of the organization of our powers. And now, after this preparation, one can say that now our random variable alpha has the following expansion. I just unite the same degree of Hermite products of Hermite polynomials and get the expansion 0 to infinity Cn of xi. Okay. Moreover, now one can check the following properties. And that, the first one, expectation of eta is equal to C0. This is just number. The second one, the expectation of eta square will be equal to the sum from n equals 0 to infinity. I am writing just summation over one index n due to the fact that summands are orthogonal. Summands are orthogonal. We collect, as we discussed, the products of Hermite polynomial of fixed degree n in every summand. So under different n, these products where this collection are orthogonal. Yeah. So here we have n factorial, and here we have. Let me write it, and then firstly, and then I will explain where this norm of Cn square. Oh, excuse me. Cn square and norm is equal to the sum from k1 kn equal 1 to d c k1 kn in square. Yeah. And let me emphasize again. like property 3, but it is included into construction, that Cn is symmetric over all variables. Okay, so we have such an expansion, and we know what is stochastic exponent. Now it's time to check what happened with the transform which we define, and go to the to infinite case. First of all, let's check again what is this transform. By the way, now from now we will call this transform. Let me write it again. Is equal to expectation of eta multiply on e of x. This is a Fourier Wiener transform of eta. Now let us find another good form of this transform. This good form comes from the expression of eta of stochastic exponent, and the fact that now one can calculate this expectation explicitly in terms of representation of eta as a function. Let me recall you that now f is a sigma of xi1 xi d. So one can check that eta has a representation like f of xi1 xi d. This is theorem from course of probability theory. And then I can continue these calculations. It is like E f of xi. Here is exponent of x xi minus norm of x square over 2. And it is equal to the following integral. Now I use the fact that our vector xi has a density. So this is integral over Rd. F of y. Here is exponent. Here xy minus norm of x square over 2. Now I am writing density 1 over 2 pi d power multiply on exponent. Here is minus norm of y square over 2, and this is dy. Now let me collect these two exponents together. Yeah, it is very convenient now, and it is equal to integral over Rd. Here is f of y. Here is exponent, and please check that this is exactly equal minus, here is norm of y minus x square over 2. And then dy. Yeah. Here I use the fact that that we consider Euclidean norm and Euclidean scalar product, and the norm in square is exactly the scalar product of the vector onto itself. So we have such representation. Now let's continue and do the change of variables in order to have there just one variable. Yeah. So let's continue, and we will have integral over RD. Here f of, let me put here, zeta plus x, and here is expectation. Oh, excuse me, I forgot the 1 over square root of 2 pi in d power. Yeah. Well, here is exponent minus z in square over 2, 1 square root of 2 pi in d power, and dz. Yes. Then it is equal to the integral to the expectation of what? F psi plus x. That's all. Let us consider the beginning and the end of our calculations. The beginning was our Fourier-Wiener transform, and here is the end. Since we have the following. Tau f of psi from x is equal just expectation of the f psi plus x. So we shift our random variable on the x. Now it is more or less trivial that Fourier-Wiener transform is just a convolution of the function f with the standard Gaussian density in RD. And this causes the effect of the name Fourier. Yes, because Fourier studied such a kernel convolution transformation of the functions, and get a lot of good properties of such kernel transformations. Still, it is unclear why we use name of Wiener there, but we will see in the future what happened. So we get a very nice formula for Fourier-Wiener transform in our case, and now we can go to the infinite dimensional case. So we have a good representation for square integrable random variable now, and let us try to expand this representation to the case when we have infinite number of the random variables. Let me recall that they are IID and normal, standard normal. So I still suppose that F is a sigma field generated by Xi. 1 and Xi n and up to infinity. This is a new challenge for us, because now it is not clear that we have such a good representation, which we use already. We already use heavily the following fact. Suppose that eta belongs to, belongs to L2 omega fp. In finite dimensional case, The fact that eta is measured with respect to Gaussian standard vector leads us to the such representation. We just used it, yeah? And this representation was useful not only in the understanding of Fourier-Wiener transform, but also it was useful in the following on the following step. You remember we organize orthogonal bases in which space? In L2 RD with the standard Gaussian measure. Yes, but now we have no such representation because we have no appropriate space where the sequence lives. Of course, it can be constructed, but let me tell you that it will be non-convenient. Please do as an do this as an exercise. Propose the construction of the metric space at least where the sequence psi k live. It occurs that it is non-convenient. It occurs that it is non-convenient from the following point of view. One can say, okay, let's have a space of sequences which diverge on the infinity with the fixed speed. We can fix the speed like square root of logarithm, yeah? But it occurs that this space is non-symmetric with respect to coordinate. And you remember, we want to have some symmetricity in order that there are no privileges between xi1, for example, and xi million or billion. So it is non-convenient to construct some special space for xi. But what we can do, one can try to keep Euclidean structure. So I am proposing to you the special and new construction. Let us introduce the white noise in the real separable Hilbert space. Space H. Let E A is an orthonormal basis in H. We know that if the Hilbert space is separable, it has an orthonormal basis, which is a sequence of piecewise orthogonal vectors which has length equal to 1. Then let us define for every element U, I will not write arrow already, belonging to H, define U psi by definition is equal to the product to the sum from k equal 1 to infinity. Here is uk U, E, K, Xk. Let us note that this series converge. This series converges. Indeed. Indeed. If we consider its summands, they are orthogonal. Orthogonal. Expectation of U, E, I, psi I, U, E, J, psi J is equal to 0 and I is not equal to J because of independence. And the following sum from k equal 1 to infinity expectation of psi k square is equal just sum from k equal 1 to infinity u ek square, and since uk is the orthogonal basis, is equal to the norm of u square by the Parseval identity. So we have a classical case of L2 convergence series, but let me recall you the theorem from the probability theory. If we have a series from the independent random variables with zero mean and finite second moment, and it converge in square mean, then it converge in almost sure sense. Okay, so we have convergent series, and of course one can consider such a family of such products u psi for all u belonging to H. And we will call this family by Gaussian white noise in H, and denoted by Xi. So we have such a family of random variables, and we call this family by Gaussian white noise in H properties. The first one. This random variable has a normal distribution with zero mean and norm of u square as variance. Why? Let me go back. Here you see second moment. It is exactly equal to u, norm of u square. And of course, the first moment is equal to 0 because every summand has such property. A second, u psi is linear with respect to u. Namely, if we take hu plus bv Xi, it is equal to A U Xi plus B V Xi, where U V belong to H and AB belong to R. Okay, it is trivial consequence of definition. And the most intriguing property, maybe it can be, one can say that Xi is not a random variable, random element in H. In H, it is a very serious remark, because if we consider here the definition of U Xi, it looks like one can consider here the vector, the element Xi, like sum from K equal 1 to infinity Xi K Ek. And then this is simply a scalar product and so on. But it is not true. This series does not converge. Let me prove you this. Okay. The series sum from K equal 1 to infinity Xi K Ek does not converge in H. And the reason is very trivial. The reason is that the sum from K equal 1 to infinity Xi K square is equal plus infinity. Almost sure. Please check this. Okay. So we have the following interesting and new object. This white noise Xi. It is defined via our sequence Xi K. It looks like that we have to invent the orthogonal expansion for functionals from Xi. But Xi itself does not exist. It has only traces. It's scalar products with different elements from U. It looks like a cat from the book about Alice in the Wonderland, where there are no cat. There exists only his smile. This is the same situation. There are no random element Xi. There exist only its products with different elements of our space. And next lecture, tomorrow, we will discuss the orthogonal expansion for functional from Xi and new properties of this expansion. For today, that's all. Thank you for attention. Maybe somebody has questions or comments, please. Okay, if there are no questions, then thank you for attention and bye for tomorrow.